Okay, so today's lesson, we're already on 2.3. We're almost halfway through chapter 2. I'm going to be honest, I know this section on dividing polynomials will take more of our time. I'm dedicating the entire week to dividing polynomials because it requires that much time and effort. I'd rather you guys get it than me rush through it and push you. I want to move at an appropriate pace for you. So, long division of polynomials. That's just dividing one polynomial into another. Is this something we can always do? You know, there are some cases when the numerator is rather small. It doesn't seem very useful, but oftentimes it will be useful. And we'll see a place where it's useful when we start graphing rational functions in 2.6. 2.7 is when we graph ones where we'll have to utilize a little bit of polynomial division. The division algorithm, that is just a systematic process of division. You learned the division algorithm back in elementary school. I know some of you might be like, oh, we're doing long division again. And like, oh, I hated that in elementary school. I was never good at it. We're going to review the process of long division with just numbers before we deal with polynomials. Whether we're dealing with variables or numbers, the process is unchanged. Now, thinking about it with variables, well, you know, sometimes that might get a little tough, a little confusing. I know that does add an added layer of complexity, but the process is unchanged. Synthetic division, which we will cover on Wednesday's lesson, is a shortcut that works sometimes. There are specific cases where synthetic division works, and when you get one of those cases, if you choose to use it synthetic division versus long division, you're absolutely fine doing it that way. But we have to learn the long division because synthetic division does not always work. It's just very specific cases it does. Those cases are somewhat common, at least, and you can do a lot of problems with synthetic division, but it does not always work. A great place where synthetic division shows up is the remainder theorem. So what that says, basically, if you're dividing by x minus k, whatever the remainder is actually what you would get if you plugged in the value k. So formally, the remainder of f of x divided by x minus k is equal to f of k. So basically, like, this becomes really useful. Say if I have some polynomial with really high powers, like fifth or sixth power, but I'm trying to plug in a number like 8. Do I want to do 8 to the 6th power? I mean, if I have a calculator, that might be okay, but that's going to get really big, right? Synthetic division, using the remainder theorem, can let us do it actually in a rather quick manner that hopefully we can do without a calculator. Factor theorem says if we get a remainder of 0, what you divided by is a factor. So let's just look at the idea of division. So when I'm dividing, so the 6 goes on the outside, the 783 goes on the inside. So if you recall from regular division, how many times does 6 go into 7? Good, once. So I put a 1 up here. Then I would do 1 times 6, that's 6. And then we would subtract these, right? 7 minus 6, 1. Bring down the next number, an 8. Okay, how many times does 6 go into 18? 3 times, good. 6 times 3, well, that's 18. That's why you guys said went in 3 times. And then let me keep my colors consistent for each step. So that was to multiply. 3 times 6 is 18. And then we subtract. And in this case, I get 0. Bring down the next number. Does 6 go into 3? No, so we would put a 0 in there. Zeros are going to be less common, not impossible in when we're doing polynomial division. But I got to tell you right now, that's going to be pretty uncommon. So that goes in 0 times 6 is 0. When I subtract, that gives me a remainder of 3. Now, in elementary school, you might have just said, oh, remainder 3, right? If you recall, you could also write as a fraction 3 over 6. And that's how I'm going to write it, as 3 over 6. So that means my answer, 3 over 6, would reduce to 1/2. So 130 and 1/2. That's long division, right? You guys are kind of, look, I know it's been a while since you've seen that process, but based off of how I'm seeing the reactions in the class, seems like you guys are okay. I remember that general process. Might need some practice with it, but hey, I'm kind of remembering those steps. So, when dividing polynomial by another polynomial, the remainder is equal to 0. That means it divides evenly into that. So if we get a remainder of 0, it divides evenly, just like we would say with numbers. If they do not divide evenly, the remainder is not 0. And we would call that an improper like fraction. And if they divide evenly, that would be more of a proper fraction. But those definitions are as critical to what we're doing right now. So there are a few things happening here. I want to divide these. This example is going to be rather tough here. A lot of the work I'm going to give you is not as hard as this example. Okay? Just wanted to throw that out there. But the process is unchanged. We want to divide these. This is 3x cubed plus 4x minus 2 divided by x squared plus 2x plus 1. Do you guys notice anything missing in this x cubed expression? Is there any term missing? There's x cubed, x number. X squared is missing. Is it possible to do this without a 0 placeholder? Yes, it is. However, you're going to get stuff looking a lot messier if you don't put in a 0 placeholder. You're going to have to think a lot harder. Putting in a 0 placeholder is critical to make everybody's life easier. So I start with writing this. X squared plus 2x plus 1. No terms are skipped there, no 0 placeholders needed. Divides into 3x squared, x cubed plus 0x squared. Because there's no x squared term, I'm calling it 0x squared. plus 4x minus 2. So that 0 placeholder is going to be there. Think of it like if I had a number like 105. You wouldn't skip the 0 in writing 105. We don't want to skip the x squared on this. So what do I have to multiply x squared by to get 3x cubed? It's going to have to be an x, and then because it's a 3 in front, it's going to end up being 3x. Yes. Oh, yes, yes. So here's what I'm going to do. 3x has to multiply everything right here. And the convenient part is, because now we put the 0 placeholder, all our like terms will line up perfectly. 3x times x squared gives me 3x squared, or x cubed. 3x times 2x will give me a plus 6x squared. 3x times 1 plus 3x. X cubes line up, x squareds line up, x's line up. Okay, now I'm going to subtract. 3x squared minus 3x squared, they conveniently cancel. 0 minus 6 will give me negative 6x squared. 4 minus 3x is going to give me a positive 1x, and then I'm just going to bring down the minus 2. Here's a place I need to pause. Do we have any questions? Do we need anything reiterated? I don't care if it's the red, green, or blue step. Please let me know right now if there are any parts that are a little confusing for you. This way I can re-explain them or redo them before we repeat the same process. This is one loop of the process. You just keep doing this until you can't do it anymore, until you run out of numbers to bring down. But that is the process. That's our algorithm. That's our loop we're going to keep going through. So any questions, please put them in the chat. In front of me, you guys look like you're okay. Okay, let's get going on repeating the same idea. What would I have to multiply x squared by to get negative 6x squared? Just negative 6. Good. So now I need to do negative 6 times everything in front. Negative 6 times x squared, negative 6x squared. Conveniently the same thing, so they're going to cancel. That was the whole point of that. Negative 6 times 2 will be a negative 12x. And negative 6 times negative 1 is negative 6. Sorry, my mask moved on me. Let me tighten this one up. I think that's part of the issue. There we go. Okay. So here with this, now we need to subtract. Just be careful on this subtraction because we're subtracting a lot of negatives. So minus a negative actually turns to plus. So the 6x squareds cancel. 1 minus a negative 12 is the same as 1 plus 12, really. So that's 13x. And negative 2 minus a negative 6 is really plus 6. And that's going to be where am I? Sorry. Negative 2 plus 6 is a positive 4. Now, I have nothing left to bring down, right? So now it's just a matter of writing our remainder. So that's going to be plus, then I'm going to put this in the numerator, 13x plus 4 over what I divided by. I'm going to tell you right now, this is a difficult example. I believe on the homework, the problems I chose for you, should it be as difficult as dividing by a trinomial? I believe they're all divided by a binomial, which just makes life a little bit easier. It might make the division a little longer, but it makes the idea a little easier. Any questions on this right now?
I have a question.
Yes, of course. Let me get the virtual question that I got you. I'm listening.
Can you go back like 2 steps, please?
Before I wrote the remainder?
Yeah, please.
So like when I did my subtracting or when I did my multiplying of the negative 6?
Well, you did the multiplying the negative 6.
Okay. And where's your question?
I was going to ask that, can we also like look for the zeros of the same side and then just cancel everything? Can it, is that also an option?
Actually, say it one more time for whatever reason.
Can we look for the zeros of each side, the two equations, and just cancel out which one?
Okay. Okay, so question I'm getting here is basically, can we factor it and see if there are any common factors that cancel out?
Yeah. Is that also an option in some?
Not necessarily for the polynomial division. We will utilize that when graphing rational functions, though. So most of the ones I'm giving you for polynomial division, that won't happen. You won't get common factors too often. But if you can figure out how to factor like a big polynomial and see that you have one factor that matches, yes, you could cancel them out and that will work. But most of the time I'm giving you a remainder. So back to where I needed to kind of restart from here. So I'm just going to undo. Whoa, that did not go the direction I wanted. Undo. Just going to undo the work from multiplying by negative 6. So I'm just going to restart that. So I remember we noticed a negative 6x squared and x squared. To get them to match, we have to multiply by negative 6. So negative 6 times x squared gives me a negative 6x squared. That gets them to match, so they're going to cancel. Negative 6 times x squared, as I had just stated, negative 6x squared. That's what we want. That's what will get us to cancel out, and what we need to drop out drops out. Then I do negative 6 times 2x. That gives me a negative 12x. Negative 6 plus 1, that gives me negative 6. That's fine, that's fine. Are we good on my multiplying right now?
Yes.
Okay, good, good. Now we're going to subtract this. And this does a lot of like minus a negative. So remember, minus a negative is actually a plus. So negative 6x squared minus a negative 6x, that's really like plus 6x squared. Oh, negative 6 plus 6, they conveniently cancel. That was the point. 1 minus a negative 12x. Oh, wait, that's really 1 plus 12x. So that's going to be 13x. and -2 minus a -6, well, minus a -6 is really +6. -2 plus 6 is a +4. Any questions on my subtracting?
No. Thank you.
Okay. Now it's a matter. This essentially is my remainder, 13x plus 4. If I had a remainder of 2 when I was dividing by 5, I could write that as a fraction 2/5. That's what I'm going to do here. This is my remainder. It's fancier looking than just a remainder of 2, but it's a remainder nonetheless. So that could be 13x plus 4 over x squared plus 2x plus 1, because that's what I divided by. So like I said, if I got a remainder of 2, I was divided by 5, that'd be 2 over 5. Here I got this fancy looking remainder of 13x plus 4. That's the top. I was initially divided by, instead of 5, it was x squared plus 2x plus 1. So that's the bottom there. Any questions about that one?
No.
Okay. So thank you guys for those questions, for making me go back and re-explain where you got a little confused. That was great. Let's look at the, oh wait, you got your picture of it? Okay. These are posted. Again, if you need to capture a screenshot quickly, go ahead. And then we'll move on to the next example in about 30 seconds. Okay, let's get going here. This one's going to be a little bit easier. I don't know if it goes in evenly. No, it won't, because that's not factorable. But if I could factor this to have an x plus 1 to get to a point that was made in the class, could I just factor both and cancel? You could. However, that's not going to happen here. That's why, I'm kind of just focusing on doing the long division. So x plus 1 goes on the outside. X squared plus 3x plus 5. Now this conveniently does not miss any terms, so I don't have to worry about my zeros. Okay. Let's see here. Red, green, blue. Okay. What do I have to multiply x by to get to x squared? Awesome. Thank you for that person to message me privately. That's great. I'll get it graded hopefully sometime today. What do I have to multiply x squared or x by to get x squared? Just x. So it's x up here, and then I multiply. So this times this, and to the 1. So x times x, x squared. X times 1 plus 1x. And then I subtract. X squared times x squared conveniently cancel out. Again, that's the point. You want that first term to cancel out every time. Then I'm going to do 3x minus 1x. Actually, let me write that just slightly clearer. So this was x squared minus 1x. Because it almost looked like it said 4x there. So again, these conveniently cancel. 3, that should be a plus 1x, now minus 1x. 3 minus 1x is 2x. Bring down the plus 5. Pause. Any questions right now? So people are shaking their head here. I'm trying to give people virtually a second as well. Now we're just going to repeat the process. That's it. We just repeat the same algorithm or process. So what would I have to multiply x by to get 2x? That's just going to be 2. So plus 2 up here, 2 times x, switch color, two x. 2 times 1, that's a plus 2. So now I just subtract them. So 2 minus 2, they conveniently cancel. 5 minus 2 is 3. So in this case, I get a remainder of 3. So that will be added onto the end plus 3 over x plus 1. Any questions about this example here? So what's in red is my answer when I divide them. It had a remainder, so it did not go in evenly. So as somebody had said, like, oh, can I factor and just cancel out common factors? Yeah, that'd be great if there was no remainder, but when there's a remainder, we're gonna have to go through this process. Not seeing or hearing any questions. So let's move on to our last example. This example here is one that we could not use synthetic division on, just like the first one. This one we technically could have used synthetic division on once we learned synthetic division. It is set up appropriately for it. This one is not. So again, that's seeing a 2x here, and what I'm dividing by, no good. It just needs to be an x to use synthetic division. So here with this, am I missing any terms between x cubed and minus 1? An x squared and an x, so make sure to put in those 0 placeholders. Again, if you're really careful, you can do it without the 0 placeholders. However, I don't care how confident or good you are. I find it so much easier and better to just write in the 0 placeholders. It helps prevent silly mistakes. So 8x cubed plus 0x squared, because there was no x squared, plus 0x, because there was no x, minus 1. Okay. What do I have to multiply 2x by to get 8x cubed? Okay, so 2 times 4 gives me 8. And since it's an x, I need to get all the way up to a cubed, 4x cubed, or not cubed. You said square. It is square. Okay. Now I'm going to do 4x squared times both of these. 4x squared times 2x gives me 8x cubed. Again, conveniently they match, so they will cancel because I was trying to get it to match that. 4x squared times -1 will be minus 4x squared. Parentheses and subtract. So those cancel. 0 minus a -4 is really 0 plus 4. That's going to give me 4x squared. Bring down the plus 0x. Looking at time, I'm just going to start moving a little faster. What do I have to multiply 2x by to get 4x squared? 2x, right? Because I need to get it all the way up to a square. And notice, this went down from squared to x, and then the next one's going to be a whole number. Okay, 2x times 2x gives me 4x squared. 2x times -1 minus 2x. And then we subtract. Those conveniently cancel, giving me this is a positive 2x, because minus a -2 is really +2. And then bring down the -1. Oh, this one's going to go in evenly. So if you could figure out how to factor this, this is a tough one to factor, initially seeing that off the top of your head. But if you could have figured out how to factor that, we would get that you do have a common factor of 2x minus 1. So what do I have to multiply 2x by to get 2x minus 1? 1, it's just what it is. So I'm just going to put a +1 up at the top. 1 times anything is just itself, so that's another 2x minus 1. Well, when I subtract these, everything cancels, giving me a remainder of 0. So this has no remainder, which means 2x minus 1 is actually a factor of this. If I wrote 2x minus 1 times 4x squared plus 2x plus 1, if I multiply them out, it will give me this. Hey, that's fine, that's fine. So that is my last example for today. I know we're running a little low on time. For your exit ticket, I don't need you to do the long division. All I need you to do is it has some missing terms. All you have to do is rewrite it with the correct 0 terms. Please do not take the time to do the long division on them. I do not check how well they're going to divide, and it's a long process. These long division problems, I usually have to work out ahead of time to make sure they'll work out okay. So the ones in the exit tickets aren't intended to be divided. Just tell me, hey, here's what my equation should be if I add in my 0 terms. That's it. You don't have to divide them for me. Saving you some time there. For homework / our asynchronous work tomorrow, 10 through 14 even on page 124. It is just 3 problems of practice, just like what I just did. That's it, just 3 problems. It's all we need to do. I know this is a long process. I know it's a tough process. This is recorded for us for that reason. So I'm going to stop the recording. There we go.